Hello, fellows. I hope you're all doing good. Today, I want to tackle how we can drive our mass balance around a reactor. For instance, a batch reactor and a CSTR or continuous reactor. Okay, so we will learn how to perform a mass balance around a batch reactor today. For this video, and my next video will be the CSTR. And this is one of the most topics in chemical reaction engineering because every reactor design begins with mass balance, and by the end of this video we will get to know what a batch reactor is, the concept of general how to we can use the concept of more general mole balance to drive the reactor equation, or how we can model the batch reactor. And also after that we tackle how to solve a numerical example, or we will tackle a numerical problem using a batch and CSTR. Okay, so let's start. So by using my general the concept of general mole balance, where we say accumulation. Accumulation is simple: mass in minus mass out minus rate of consumption. We know the reason why. So because we are dealing with a reactor, we have to write everything in terms of what? In terms of mole. Why? Because because we use more balances instead of we have to use more balances instead of mass balance in chemical reaction. Because chemical reaction changes the number of moles of each species that is taking place in the reaction, but they do not change the total mass balance. So in simple idea, we have to because we are dealing with a reaction, so it's better to write everything in terms of mole. You understand? So how can we do that? It's simple. We have to simple from concentration, because every reactant that we are going to put, there's a concentration. So from concentration, you can say concentration is simple, the moles divided by volume. And from here, we can see the mole is simple, the concentration of a specific reactant, whether it's A or B, multiplied by the volume of the reactor. By the volume, not the reactor here, by the volume. Okay. So with this concept, with this concept, we can also see that the rate of consumption is simple, the rate of the reaction versus consumption, so minus rate of reaction. The reason why it's minus because the A, we are writing everything with respect to A. The A, this A, and this A is what is a is the reactant, and the concentration of reactant will decrease as time progresses. So with decrease in concentration, we have to write it what minus. Then for this, multiply by the reactor volume. Okay. So from here, because we are writing everything in terms of mole, so we say the N A, which is rate of what mole accumulation, or we can say the rate of mass accumulation. Simple, mass in minus mass out minus what rate of consumption. But we are dealing with moles, so we will rather say mole in minus mole out, the minus the consumption, which is this one, the rate of reaction multiplied by volume. Okay, and the Na is simple by what? CV. So here which will be the V, the Ca. We are writing everything with respect to what? A, the reactant, which is equal to the in will be what? CAI, which is mean the in, and this volume now will be what the flow rate, the volumetric flow rate. So I'll write down what write it here as what F will be the volumetric flow rate incoming minus the same volumetric flow rate by the output one multiplied by what CA O mean output minus this rate of what consumption, which is simple RAV. But because I'm writing everything with respect to what CA, I have to write this one also with respect to what CA. So simple RA is simple because it's negative here, so I have to make it into the left hand side, yeah, at the right hand side. So it's simple minus this one is the rate of reaction. So for instance, if it is first order, it will be minus K CA and the volume can. So now our general mass mole balance will be V CA dt, which is simple F naught CAI minus F CA naught minus K CAV. Okay, so let's do our our balances to make sure, because mole Na, which is mole, each unit has to be what mole, and that one is what's equal to CAV. So let's do our unit balance to make sure everything is what is perfect. So concentration is simple mole per meter cube multiplied by volumetric flow rate as it is here. And that one be meter cube per second. So simple, we can see meter cube. So it's simple, we can say we can get more over second. And that one, because it's changing with respect to t, so it's correct. So let's check our rate of consumption. The K is what unitless. The C is simple mole per meter cube, and the V is simple the volume of reactor. It's meter cube. That one to give a mole. So everything is correct from here. So our equation now is what the volume of the reactor dt is simple F naught CAI minus F CA naught minus K CAV. But for a batch reactor, as we said earlier, there's no flow, there's no in and there's no out, because in input is got output is got 0. So this 0, this is 0. So we will simply get our dCA dt simple will leverage minus K CAV. So because for a batch reactor, we'll feed everything and leave it for some times and come and check our product. So to get the concentration at a specific time, concentration at specific time, we need to rearrange the equation and integrate. So we will get from here, we can see the volume will go. You understand? So we will get this the CA dt is simple minus K CA. So from here we'll rearrange and integrate. So we will get the CA over CA, which is simple minus K dt. So to get the concentration at some specific time that we are going to leave the reaction to take place. So simple, the beginning of the reaction is what? The concentration is what? Ca naught beginning where time is zero, the concentration is what? C0, C0 meaning the concentration we at the time that we put into the reactor. And that one is what? Zero. Because the time we put the concentration to the batch reactor, at the time is zero. And the concentration we are going to check is what? At time t. So now we have to integrating this Ca over this over Ca simple ln natural logarithm. So it will be ln Ca from Ca naught to Ca, which is simple minus k bracket t and 0. Okay, so we are going to get ln Ca all over Ca naught, which is simple minus k t 0 and t. Okay, by going further. Okay, so because you want this t, you have to take the inverse. So you are going to get Ca t Ca naught simple e minus k t. Then our c has some specific time symbol Ca naught e minus k t. So this is how, by using this equation, you were able to get the concentration inside the reactor at some specific time. So let me leave it here. We are going to continue with the continuous reactor.